All right, let's now talk about the GAN objective, essentially how the loss function looks like. Before we get to that though, just again the big picture overview and the important question, when does a GAN converge? Because the answer might not be so obvious. So we have the discriminator, which is trained to distinguish between real and generated images. So essentially the discriminator wants to become better at detecting these generated images, while at the same time the generator wants to become better at fooling the discriminator. Right? So in that way, there's like this fine interplay or this back and forth between the generator wanting to be better at fooling the discriminator. So it kind of wants the discriminator to make wrong predictions, and the discriminator wants to make correct predictions. So when does it actually converge if it goes back and forth? So if you train this and everything is set up properly, it should at some point reach some point of equilibrium. So in the context of game theory, that would be called the Nash equilibrium. So there will be some sweet spot between the two where both are somewhat happy. So the loss function for the GAN overall would look like this. It's essentially a min-max game. So some people call it minimax or zero-sum game. And we have two parts here. So we want to minimize some G here, where G corresponds to, let's say, the generator parameters, and the D corresponds to the discriminator. And you can see there are two broad parts here. One part is here, and the other part is this one here. And in this left part, what we can see here, that's D for the discriminator. So this is the output or prediction of the discriminator. And this on the right hand side is the output of the generator. So this is our input image. Let's call that the generated image x prime, whereas here the x is the real image. So D on x prime, this is like the prediction of the generated images. So looking at this, we have two terms. One is prediction on the real images, and one is the prediction of the discriminator on the generated images. So let's now, in the next couple of slides, walk through this step by step, looking at the discriminator part first and then going to the generator part, because there's a lot of things going on. Let's look at it one at a time. Okay, so there are lots of things going on now. At the top, I just copied over the equation from the previous slide. And now in this slide we are going to focus only on the discriminator part, so the maximization part here, the D. And since it's a maximization problem, we are going to use, or assume we are using gradient ascent. Before, in the lectures, we used gradient descent because we wanted to minimize something. Now, because it's a maximization problem here, we are going to maximize something, which is why we call this gradient ascent, not descent. But this is just a minor detail. Okay, so we are going to maximize something here. So going to, for instance, maximize this part and this part for the discriminator. So here at the bottom, showing you the gradient of the loss with respect to the discriminator parameters. So W is just the weights of the discriminator, and this is the loss. And this is something we want to maximize though, because like I said, it's a maximization problem. Oh, and by the way, we have a sum here instead of the expectation, because in the form here at the top, this is assuming the data generating distribution, but in practice we never really have access to that. We only have a fixed size training set, so this becomes more like an empirical loss. So this is why we use the sum here, where the sum is over the n training, so it's the number of training examples. Just a minor detail. The interesting part is now we are going to focus, let's say we are focusing only on this part here, and then I will have a new slide, exactly a duplicate of that slide, where we are going to discuss the right-hand side here. I want to discuss this in 2 slides because I can imagine it will become very crowded here. Okay, focusing on what I highlighted here in purple. This is at the bottom here, essentially this part, the discriminator for the real images. What we want the discriminator is to predict well on the real images, right? So we want this probability to be close to 1. So the discriminator here, which color should I use? Red. So the discriminator here is outputting a score between 0 and 1, representing the probability that an image is real. So it's outputting this probability here between 0 and 1. And ideally, the best possible score for the discriminator, because it's a maximization problem here, is this to be 1, right? Because if we plug in some values, so there's a log here. So log of 1 is, let me do it like this. Log of 1 is 0, and a log of 0, that would be the worst case, would be minus infinity, right? So the worst case would be when we predict a 0 for the real images, and the best case would be to predict a 1. That's how we maximize this term. Okay, so the next slide, let me show you the second term here. All right, let's do this again. But now we are going to focus on the right part. So we are going to focus on this one here. And we are still talking about the discriminator. So still talking about gradient ascent maximizing something. We're still talking about maximizing something. And now we are exactly here where we consider generated data. So G here is the generator, and it receives some noise input Z, and it will output X prime, the generated image. If we look at this term, it's actually very similar to what we have on the left-hand side. So there's also a D, and the D still outputs a value between 0 and 1. But now, of course, based on the generated image instead of the original image. And now we have this 1 minus here. So as a consequence, what happens if our discriminator is very confident that this image is a real image? If it thinks this is real, it will put out a value close to 1, right? So in this case, let's go over here to the left-hand side. So log 1 minus 1, this is if it thinks it's real. So this would be log 0, which is minus infinity. It would be a very bad loss, because the bigger the better, because we are still here talking about maximizing. So the worst case scenario is that our discriminator thinks that the generated image is real. We're talking about optimizing the discriminator, so we want to actually avoid that. To maximize this term, we would put in, or the discriminator would predict a 0, right? So because then we have log 1 minus 0, which is log 1, which is 0. So this would be our best case scenario for predicting generated. So here I mean with a value of 0, this is a low probability for real. If we set the cutoff at 0.5, this would be essentially predicting generated. Okay, so putting these 2 points together, what we want for the discriminator when we are training the discriminator here is we want that it outputs a probability close to 1 for real images. And we want here it to output a probability close to 0 for these fake or generated images. So this is the discriminator part. In the next slide, we will then focus here on the generator aspect. All right, so finally we are now finished with the discriminator, and we can now focus on the generator update. Okay, so now we are talking about a minimization problem. So we can use gradient descent for training the generator. We are focusing again on exactly the same part as before. However, before we updated the weights of the discriminator, now we keep the discriminator as fixed and update the weights of the generator. It incorporates the prediction of the discriminator, which is why I circled this whole thing here. So looking at the equation above, if we want to know what we have to update for g, so the left term, if you think also in calculus of the sum rule, this would be kind of cancelled because there is no g here, right? So this is not relevant in the loss. So we can actually ignore this for now. So this has nothing to do with the generator. On the right hand side, we see the generator here. So let's bring this down here. This is again the empirical loss, so on the training set. And this is exactly the same I showed you before on the previous slide, except now we are talking about G instead of D. And we are talking about minimizing instead of maximizing. But again, this part is still the generated or fake image. And the discriminator here predicts on this fake image, and the output range is still between 0 and 1. Where this represents the probability for real. Okay, so in the previous slide, when we talked about the discriminator, we wanted to maximize this. So we wanted to maximize the probability that the discriminator predicts real on real images and predicts fake on these generated images. So let me write this part, log 1 minus. So in order to maximize this in the previous slide, what we had is, or what we wanted the discriminator to output, wanted it to output a 0 here. Because then we have log 1, which is 0. That was our best case scenario for maximizing the discriminator. Now, since we talk about a minimization problem, we want actually the discriminator to output a 1 here, because then we have 1 minus 1, which is 0, which gives us minus infinity here. Minus infinity is, yes, you can imagine the lowest possible value, right? Because we talk about minimizing this loss term, gradient descent, minimizing. So we have minimization here, and this is minimized if we have a log 0. So if the discriminator outputs a low probability here, a high probability here for real. So the discriminator here, this is P. The probability that the image is real, which is in the range between 0 and 1. It is a generated image, so it is not real, but we want the discriminator to think it is real. So we want it to output a high score, a 1, because then we have 1 minus 1, log 0, which is minus infinity. And that is how we minimize the generator. So the generator wants the discriminator to output the prediction that something is real, although in reality it's not real. And yeah, this is then now the different parts. We covered the maximization of the discriminator, and we talked about minimizing the generator. So in the next couple of slides I will just add a few more things from the paper. So this here is a screenshot from the original GAN paper. So this is the training process of what we've discussed in the previous slides, just summarizing it into this training procedure. They call this the mini-batch stochastic gradient descent training of generative adversarial nets. Of course, also gradient ascent is involved, as you have seen in the previous slides, for training the discriminator. In fact, in the next video I will show you a trick that we can turn this ascent problem into a descent problem. It's also recommended in practice, but for now let's stick to this original outline of the algorithm here. So let's discuss this step by step. There's a for loop here. Let me stick with green here. There's a for loop here for the number of training iterations. You can think of it also as for loop over the number of epochs. And Then there are the discriminator training and the generator training alternating. So let me box this in so it will be easier to see. So this is the the discriminator training. And then here at the bottom, this is the generator training. Okay, let's take a look at the discriminator training first. So it says for k steps, and the k steps is a hyperparameter, and they used k equals 1. So they only essentially train the discriminator once, and then they go to the generator, and then they go back to the discriminator and so forth. But in practice, you could update the discriminator several times before you update the generator. It's another hyperparameter to consider. What we do is when we train the discriminator is we sample a mini batch of m noise samples from, let's say, a standard normal distribution. And then we sample a mini batch of m examples from the data generating distribution. Here, this is essentially our training set. So this is essentially just drawing a mini batch. So there's nothing special about that. It's just obtaining a mini batch. And then we update the discriminator by ascending its stochastic gradient. So this is what we talked about in the previous slides. That's how we update the discriminator. So this is the discriminator part. At the bottom we have the generator part. Again, here we sample a mini batch of noise examples. And then we update the generator by descending. So here that's the SGD that we had on the previous slide. And yeah, for learning, so this is it essentially. And for learning, they say they used momentum-based stochastic gradient descent. Personally, I also had good experiences with SGD and momentum and Adam, but I've had seen some comments or people recommended not using momentum because you want the generator and the discriminator to be kind of flexible. So the momentum term makes them lag behind a little bit. So sometimes people recommend not using momentum, but I find that it works just well with momentum as well. Yeah, just to recap, GAN convergence. So when does a GAN converge? Like I mentioned briefly before, it converges when we reach the Nash equilibrium, which is a term from game theory. And that is essentially, when we have an equilibrium between maximizing the loss for the discriminator and minimizing the loss for the generator. So in the game theory jargon, it is basically reached when the actions of one player won't change depending on the opponent's actions. And here concretely, this means that the GAN produces realistic images. So the generator is able to produce realistic images, and the discriminator outputs random predictions, probabilities close to 0.5. So the GAN is able to produce images that are indistinguishable from the training set images. I mean, they're still new images, but they look very realistic, while the discriminator can't tell them apart. The discriminator essentially predicts 0.5, like a 0.5 probability, being unsure whether something is real or fake. Yeah, so here's another figure from the original GAN paper. This is a really nice figure illustrating the GAN training process, so when it converges, when it reaches the Nash equilibrium. So there are 4 steps to this figure, A, B, C, and D. Let's talk through this one by one. So let's focus on figure A first. You can see there are multiple lines. That's a lot of things going on. So let's annotate this first. So what they say here is in the green solid line is the generative distribution, or essentially the generator data. So the outputs of the generator, or let's say the fake images. Then what we have is here in black, the black dotted line, these are the data generating distribution. So with this, it means the original training set images. So let's just call that training or real images. Then we have one more line, the blue dashed line here, and this is the discriminative distribution. So you can think of it as, here's this one, it's maybe not ideal, let's do it like here, discriminator. Predictions. And you know, from the previous slides, the range is between 1 and 0, where the discriminator outputs the probability that an image is real. Okay, so now we have these different things, and you can think of the black line here as the probability density, and here this is the X, the input images, so the range of the input images. Of course, it's only a one-dimensional plot here, just for simplicity. X are the input images and Z are the generated images. Let's say real and generated. And what they're trying to show here is where the generated images map to, and you can see that, let's say, the training images, the density is highest in this region here, and the generated images at this first step, they are mostly mapping only to a small region over here. So the highest density for the generated images is here. And they say this step A here is near convergence. So it's not quite converged. So they are illustrating here the process of converging, going from A to B to C and to D. So we said that the distribution of generated images here is different at this point from the training distribution, but it's not substantially different. The discriminator predictions are very confident here for these images, like that they are real. So here in this whole region, the generator predicts real, except then when we go down here to the generator images, here the 0, it essentially detects correctly that they are fake. So this is a region in general where the discriminator is pretty happy, it's doing good predictions, but the generator is not very happy because it's not able to fool the discriminator yet. So next in B, so where's B here? B, in the inner loop of the algorithm, D is trained to discriminate samples from data. So now we have a training step. So B is a training step updating the discriminator. So you can see after this update, it will become even more confident. So after this update, so in step B, now it's consistently around 1 instead of being fluctuating here. And you can see also here in this region, it's consistently around 0 instead of being fluctuating here. So here, this updated the discriminator. After the discriminator update comes the generator update, right? So now we have a training step of the generator here in C. After this step, what you can see is that the generator learns how to make the distribution of the generated data in green here closer to the training data. So they are now more similar to each other. And you can see then that in this region, the discriminator is somewhere like very confident. So it's in this case, the discriminator is not doing so well anymore. So here, this is a point in C where the generator is more happy, and in B, the discriminator is more happy. But in what we want is we want to find this equilibrium where both are having the sweet spot where both are relatively happy. So this is reached in D when you do many steps. So in D after several steps of training if G and D have enough capacity. So if they are networks that are able to learn, of course you can have maybe networks that are too weak to learn anything useful, then of course this would not be the case. But if both have the capacity to learn, they will reach a point at which both cannot improve, because the data generating distribution is the same as the generator distribution. And the discriminator will be unable to differentiate between the two distributions, outputting 0.5 as the prediction. So this is what we can see here. So here we can see the generator has learned to output or to recreate the training set distribution, and the discriminator will be unable to differentiate between the two. So here steps A, B, C, and D kind of illustrate the process of training GANs, at least conceptually. In practice, it's way more messy. It's not so easy to reach step D. But yeah, this will be more clear, I think, when we look at the code example, how difficult it is to train a GAN. In any case, now we covered the loss function and the GAN objective, the convergence and everything. And in the next video, I want to briefly tell you about a small modification so that we can use stochastic gradient descent for training both the generator and the discriminator, and also how we can improve the gradient, the loss gradient for the generator.